Yes, thank you everybody for joining today. I'm really excited to share some of our experiences with you around IMU validations in biomechanics, and particularly on how important kinematic models are for the validation outcomes. Just by way of quick introduction, my academic background is actually in biomedical engineering, and in my postgraduate studies, I specialized in 3D motion capture technologies in sport and clinical settings. And I see myself as very privileged to have a job I really enjoy, which is to manage a human movement analysis laboratory full-time in my home country in South Africa. And I've been working in this field now for around 12 years, and I've been lucky enough to work with many different IMU motion capture systems and companies over the years. IMUs are really fantastic because they can get us out of the lab into more natural environments, and they make it more cost effective for us to scale up the number and the length of experiments or tests that we want to do. The question remains, however, how well does this technology actually work? How well does my specific IMU product work? Clearly, these are important questions that we need to be equipped to answer. Many new buyers often look into the scientific literature for validation results and studies, and it's not uncommon for them to feel a little underwhelmed by the lack of an exact sort of match for what they're looking for in the literature. IMU validations are really quite intense and technically complex, so there aren't as many as you might think. And many people might also, on the other hand, feel overwhelmed by different studies offering different conflicting results. Sometimes the IMU performance might seem unrealistically good or sometimes disappointingly bad. And many times it seems extremely difficult to interpret the results or reach a satisfying conclusion. So you often see after buying their own IMU system, many researchers start off with their own validation study if they have gold standard equipment around, like a 3D camera system to compare it to. But yeah, for this webinar, really, whether you're interested in just reading other validation studies for IMU technology or whether you're conducting one of your own, I really hope that this webinar helps just to highlight some of the key factors that we should all keep in mind when dealing with this topic. So the way I want to structure this is I want us to walk through the way our facility performed a recent IMU validation study. And we're going to look at details around sort of how we went through these different factors, how we considered them, the modeling that we did, the measurements that was done, the experiments we chose, and how we analyzed the data. So we'll have a look at some data in the live interactive portion of the webinar, and I'll also go over some results and some of the metrics that we used in our study. So just to start off with the measurement quality, for obvious reasons, it's very important to understand the factors that are affecting measurement quality in a validation study. And we're not going to focus so much on this topic today, but I want to encourage you all to check out the previous webinar in this series, which goes really into some detail on this topic. But for today, it's really just important to note that depending on cost, and the type of test environment and human movement involved in the validation, the sensor components or hardware really make a massive difference, or they can. And like, for example, the IMU in a cell phone or a low-cost IMU kit cannot be expected to perform as well as a premium IMU in a motion capture, compared to a motion capture system. So, also, IMUs have code running inside of them that can drastically affect how accurate each sensor signal is in terms of the engineering side, sort of things like sensor calibration, how well synchronized the data is between different sensors in one IMU, and how synchronized a group of IMUs are in terms of their measurements and timing. I mean, I've seen, for example, some IMUs that have drifting sample rates. Sometimes they're measuring at 190 hertz, sometimes 210, even though the specification says 200 hertz measurement sampling rate. So these are all the kinds of things that the firmware handles, and the firmware in top-end IMU systems solve a lot of these problems that are inherent in off-the-shelf hardware. IMU systems use sensor fusion algorithms as well to track the motion of the IMU, and different algorithms have different levels of accuracy. They have different levels of robustness to deal with difficult measurement scenarios like magnetic disturbances or shock and vibration. But essentially, once you've bought your IMU system, it's just critical to work skillfully within the limitations of the hardware, the firmware, and the fusion. And this will affect how you do validation testing with the system in terms of the protocols that you choose, the activities, the environment that you do the testing in, how you set up your subjects, and so forth. So IMU validations can be done at many levels. You can validate the hardware or the firmware, sort of things like gyroscope signals and accelerometer signals to see how valid they are. You can validate the fusion to see how well a sensor is just tracking itself in terms of its roll and pitch and course angles. But most of us here are probably more interested in what kinds of things we can do with IMUs and a kinematic model. So in our validation study, we were at least interested in the postural output from an IMU system, things like joint angles, segment angles, and so forth. But of course, once you've got a kinematic model, some systems might offer additional information like position or translation information. That would be things you could validate like step lengths, whether distance traveled over the floor is accurate, and so forth. There's also a bunch of additional information that you can get, such as things like foot contact detection, and this obviously opens up things that you could validate in spatiotemporal data, such as contact time, cadence, gait speed, and so forth. But we're really focusing in this webinar on the postural information that we were looking at in our study. So it's important to mention here that the most popular reference systems used in IMU validations are 3D optical motion capture systems, because they allow for unrestricted movement and provide very accurate orientation tracking. So we did this in our study. We were validating an Araxon IMU system, and we used our lab Vicon system as well for the reference data. We also chose a space that was magnetically clean for where we did our calibrations and where we captured the data. So you'll notice we have a wooden floor and so on. And this is all part of our best practices that we applied to the study just to get the best out of our IMU system. So we've looked at the fact that the error sources need to be well managed and that optical motion capture is the preferred reference system. But one of the most important factors to look at next is the technical frames used with the optical system. Now, many of you might be asking, what is a technical frame? Which is a fair question. And so technical frames are one of the 3 foundational coordinate systems or frames in 3D motion capture. And this is really the framework for understanding all the topics in this webinar. So if you forget everything else, please remember this. Every motion capture system has one reference frame, which we call the world frame. And that's usually stuck to the floor. And so for IMU systems, this is usually an earth frame pointing north, east, up, and optical systems usually have a predefined laboratory frame. Sometimes these systems use what is called a progression frame for the world frame as well, where one of the floor axes points in the direction the person is moving or facing. The technical frame, on the other hand, is the coordinate system that's stuck on a body segment, and it's the coordinate system that the motion capture system tracks. So for an IMU, it's the axis directions, usually painted on the housing of the IMU on a sticker or something, in which the accelerometer and the gyroscope and the magnetometer signals are measured. So this would be a coordinate system like this. And then there's a third coordinate system called the anatomical frame, which is used to describe the planes of motion on each segment. So for example, for the femur here, we have a green axis, which is indicative of the flexion extension axis of the knee. And these are the anatomical frames are the ones used with modeling techniques to produce joint and segment angles. Obviously, each bone needs its own set of technical frames and segment frames, anatomical frames, so that we can get things like joint angles. Now, in a validation study, you really have to keep your wits about you a bit, because there are actually now double as many frames. So if you choose to use an optical system, it has a different world frame to the IMU system. Not only that, but there are two different technical frames on each bone and two different anatomical frames for each bone. And it's important also just to note that optical systems usually construct the technical frames differently, obviously, to an IMU system. An IMU system measures the technical frame directly, whereas in optical motion capture, we need at least 3 or more markers to construct a technical frame. So one of the most important things that is often overlooked is, well, not one of the most important, but an important factor in tracking these technical frames with cameras is the size and the shape. And this is tricky because usually they're attached sometimes to the skin, and now in a study like with an IMU system, it's sometimes stuck to another object, sometimes even the sensor. So it's important to keep in mind that the bigger the cluster is of markers, the better the tracking. And also to keep the markers from being collinear is very important. So it's also advised to make sure that they don't form a thin plane in space. One of the decisions we made was to stick our technical frames together like this. And so we actually 3D printed a plastic bracket that allowed us to screw the markers on and to glue the sensor in as well. And this is quite common in validation studies these days to basically make sure that the soft tissue artifacts are the same for the two systems. So it doesn't remove the soft tissue artifact from the data, but it makes sure that there's no difference in soft tissue artifact. Because otherwise what happens is, even if both systems work perfectly, if the IMU is not stuck to the cluster of markers, there'll be a difference in your data simply due to the fact that the two technical frames move differently relative to the bone. Of course, this can reduce the ecological validity of the data because these motion capture systems are not usually used like this. So the data might not be ecologically valid if you're thinking of using the results for something other than validation, but we weren't really interested in that, so we just stuck them together. The next step, after we've decided how to set up our technical frames, is really what I think of as the most crucial factor in IMU validations. And this is that we need to consider how model calibration is done for the two systems. How do the two systems register the anatomical frames? Now, how is this typically done? Well, each anatomical frame is defined using 3 axes, which are usually obtained in an initial standing posture like this. And you basically you have a primary axis for each anatomical frame, which is usually a longitudinal axis of the bone. You have a secondary axis, usually lateral, and a tertiary axis, which is usually calculated, usually anterior-posterior. Now you can get these axes using anatomical landmarks, which is the ISB recommended approach because it's a person-specific calibration then. For example, if you wanted to get the anatomical frame for the femur, you'd use the hip center and knee center, which are these yellow marks here, and you'd use them to get the primary axis like this. And the knee center and a lateral condyle marker then would be used to get the secondary axis like this. Now the secondary axis is called the secondary axis because it is forced to be perpendicular or 90 degrees to the primary axis like this. Now the tertiary axis is then just simply calculated from the other two. An important thing to note here is that some anatomical points can be measured outside of the body, while others need to be calculated because they're internal points like the hip center or the knee center. These calculations also can differ between modeling approaches and can influence validation results. So this is something important to track in a validation study. Now, what if you can't use landmarks for calibration? Now, this is sometimes the case. So there's another popular method that has been developed. Oh, sorry, I just missed this point, that basically you can see here a good example of how the anatomical axis of the pelvis is now tilted for an anatomical calibration because the red axis there is not perpendicular to the ground because the anatomical points are not at the same height. So what you see here is that there's some natural tilt in standing, pelvic tilt, and this translates into some hip flexion by definition, which is something you won't see in a calibration that doesn't have landmarks, and I'll illustrate that now. So if you don't use landmarks for calibration, there is another popular way, which is called a static reference pose. And this assumes the direction of the axes are basically in a generic position of neutral. So all the axes are perpendicular to the ground, parallel to the ground, and the vertical axis is straight up for each anatomical frame. Now, how valid and reliable are these calibrations? If we briefly survey the literature on this issue, it becomes clear quite soon that model calibration really matters, even when we're comparing data just from gold standard motion capture systems. This is a study, a really nice study done by researchers from Griffith University in Australia. And what they found is that depending on the post-processing you use, some joint and segment angles, such as the pelvic tilt you see there in the one graph, or hip rotation, can differ by more than 10 degrees based on identical measurements just from an optical system, which is our gold standard system. And their conclusion was that over 90% of these quite large differences in some cases were due to modeling. Over 90%. And more than half of them, the red there, are due to differences in model calibration or anatomical frame definitions. So that's quite a significant finding, illustrating that modeling really matters. Even when you've got exactly the same measurements, it can make a big difference. Now, this is also really important to note, because it means that you have to be careful about what modeling you're doing with your optical system in an IMU validation study, because it's your reference data. So, I mean, optical systems are very accurate at tracking technical frames. And so what we see here on the right is a picture showing the kind of normal range of error or uncertainty you can expect for tracking a technical frame using an optical system. In other words, your measurements and your measurements of the IMU orientation. And what we see is that optical systems are comfortably in a normal range where they're used in the correct way, comfortably lower error than 1 degree per axis. But modeling done with these technical frames can really affect results, depending on which model you use. And you don't want to, in a validation study, simply assume that the differences are due to the IMU system measuring incorrectly. So what we can see also is that IMUs can be very accurate. It's just that we know that they can be slightly less accurate in difficult scenario test situations. But we see a normal range of accuracy for high-end IMU systems of within 1 or 2 degrees per axis. Now, what we see on the picture now on the right is that basically ISB compliant landmark calibrations are quite reliable, and they're quite standardized, and this is why they are recommended by the ISB and are recommended for validation studies. But it really is the modeling that makes the difference, because if an optical system uses landmark calibrations, the uncertainties are relatively low. But if it had to use a non-ISB calibrated model, these are the kind of differences we saw in the study that I just referred to. Now, the problem is that IMUs can't really measure landmark positions, and so they're forced to use static pose calibrations. Now, this is fine for some angles, but other angles are less comparable to the gold standard simply by definition. So if an IMU system is using a static pose calibration, some angles such as the knee flexion might be really comparable to an optical system, but some other angles such as hip flexion, which I showed you in the previous slide, might be very different. What we really want is to try and get IMU systems into that green zone for their measurement quality, and what would be really cool is if we could have a landmark calibration that we could use with our IMU systems. I just want to say that if you're using a static pose calibration with an IMU system, it doesn't necessarily mean that the angles are not useful in practice. It simply means that they will score badly in a direct comparison to a gold standard optical system in a validation study. Now, we also see in the literature that one of the references for how inaccurate we can, or what is the minimally clinically important difference in validation studies, usually the value that's used there is around 5 degrees, because it's believed that this value would, any difference in two systems that's greater than this value would be quite likely to lead to a difference in clinical decision making. Now, some studies get around this idea by validating their IMU system using the reference system in their validation study. So they'd use the optical camera system to calibrate their IMU system, which usually works quite well. Of course, this means the validation results are not really indicative of the results you can get with the IMU system outside of the lab or without an expensive optical system to calibrate them. So this is really where our study came in, because we were interested in validating an IMU system using a portable device for landmark calibrations. So I have now, my pictures are not going to show up, but that's fine. Basically, we wanted to validate the CAT system, which I'll illustrate to you in a minute in the software. And this is a system that we demoed in the previous webinar. And what it does is it allows us to measure landmark positions on the surface of the skin, but it's a portable system, so it can be taken anywhere, which makes it usable with the IMU system in mobile applications. And the software then is using that information from that system to perform the calculations to get the internal landmarks and calculate the anatomical frames and applies it to the model. But our goal was just to validate the system against our camera system with a model that was also calibrated with landmarks. So we actually control things like the anatomical marker set, so that the two calibrations were done with the same set of anatomical points on the body. We also had to make sure that the anatomical landmarks that we used were identified similarly for both systems. And one of the downsides of our study was that we couldn't actually do the calibrations at the same time, because we had to digitize the points on the skin, and then we had to put the markers for the camera system on top of those landmarks and then calibrate again for the optical system. And so what we did, as you can see in this photo here, we put landmark markers on with pen on the skin or on the shoe or wherever the marker was going to go. So you can see here that we try to control for that so that we didn't palpate differently for the two different calibrations. And we also try to make sure that they stood in exactly the same position, because if they calibrated in different postures, even though the technical frames were stuck together, there would be soft tissue artifacts affecting the output of the two systems. So this is something quite important, that you calibrate in the same posture for both systems. So let's take a breather and just do a quick demo. I want to illustrate how we apply the calibration in the software to one of our trials that we captured for this study. So I'm just going to Zach, can you just confirm that you can see the screen?
We sure can, thank you.
Okay, so this is a database just to illustrate what I wanted to say about the calibrations. So what we have here is the skeleton of a person that we were doing a calibration by. So they were standing in a static pose, and we have what this is a static reference pose. So as you can see, the skeleton is basically positioned in a very neutral posture, which is similar to how she's standing, but not necessarily exactly based on landmarks at all. And so what I want to illustrate now is we collected using this pen over here that is a magnetic tracking system that the CAT system uses that I described earlier. This system allows us to digitize very quickly the points on the body. And the data is buried inside this file. So I'm going to go ahead and just show you how this file actually contains points that have been digitized in this space, similarly to a snapshot that you would get from a camera system. And what you can see here is that it shows a much more person-specific posture. So this is really quite a big deal for IMU systems, because IMUs can't measure these points directly, and so they need a second system to help them or to provide that information for calibration. So you would take this information and then be able to track a person-specific calibrated model during your test activities. So yeah, basically this shows that the angles that we had previously, which were neutral, are now different because we actually have exactly how she was standing from the system, rather than assuming how she was standing. So I just want to illustrate another example of this from a person who stands in a different posture than the one. So one of the things with the static pose is that you have to stand in this neutral posture. This system allows us to capture postures that are asymmetric or just relaxed. And so the static pose calibration would assume she's standing incorrectly, assume that she's standing like this, but she's actually not. And if we apply the landmarks to the calibration, we get a very accurate depiction of her posture in calibration. So the calibration is now much more user-friendly for patients and people who can't stand exactly correctly for the static pose. Yeah, basically that's just to illustrate how we can, in the software, quickly apply these calibrations to the same data to get a different modeling output for a specific trial or recording that we've taken. So we did that for all our recordings, and we were able to produce results for models that were calibrated with CAT and without CAT, and that forms the basis of our analysis. So so basically, in our outline, we've talked about model calibration and technical frames and measurement quality. The next step is really to consider how do these models compute the anatomical frames during the movement. In other words, they don't have the landmark information anymore, and usually at least, and so they are the models calculate from the technical frames, they calculate the anatomical frames using the calibration information. Now, how do models do this? Basically, what we start with is the technical frames that are measured. And the first, so there are two traditional methods basically that are used in motion capture. The first one is called direct kinematics. And this approach assumes that the technical frame and the anatomical frame are rigidly attached together. So as you can see there, one sensor provides one bone. And this is just to illustrate how this would eventually detect each bone separately for each sensor. And in other words, the IMU and optical markers are assumed to be pinned to the underlying bone, and therefore we're able to calculate where the bones are from where the technical frames are. Now, the second approach to modeling computation is called inverse kinematics. And this approach is usually more common actually with optical systems because it can be used with IMUs as well. And it assumes that the technical frame and the anatomical frame are not rigidly connected, but rather that all the anatomical frames are attached to a skeleton. And so in essence, it's a global optimization that calculates all the anatomical frames from all the technical frame data. So for our study, we chose to use a model for our reference system, for our camera system, that follows the same computing approach as the IMU system because we wanted to standardize things. So we chose a direct kinematics model, the CAST model, which is well known and supported in the literature. And CAST segments are basically independent, so they give you all the points on the bone and the anatomical directions directly from the local technical frame. However, another very popular model that we were wanting to investigate was the conventional gate model, or it's popularly known as plug-in gate in the Vicon software. And we were interested in this model as well because it's definitely not an inverse kinematics model. It is considered to be a direct kinematics model, but when you look into the details, it's not a pure direct kinematics model. Some segments, such as those on the limbs, are dependent on proximal segments, other segments, for getting some of their landmarks. So this will illustrate it for you. The pelvis gives the hip center. The hip center is used to calculate the knee center, and the knee center is used to calculate the ankle center. And so there's a dependency in the chain down the limb. This means that if the pelvis technical frame moves on the body, what we'd actually see is a dislocation of the hip center, and this would give us the appearance that the femur would actually move. So the femur would actually move for the plug and gate model if the pelvis sensor was dislocated on the bone. And yet the cast model wouldn't register anything because the thigh technical frame might not have moved at all. And so this is an important kind of illustration of how the model computations can also make an impact on the data. There are also some other issues to consider, like joint constraints and segment constraints, how joints are. So you don't want to compare a hinge joint to a ball joint in the two different models in a validation study. So it's very important to consider these things. There's also quite a hairy topic around the Euler angle sequences. All I want to say about that is that there are ISB recommended Euler angle sequences for joints, and two models should have the same Euler angle sequences to be compared correctly. Otherwise, basically, it's just a comparison between apples and oranges. So it's very important if you see big differences between models to check the Euler angle sequences. Perhaps that's where some of that is coming from. So our second goal was also to compare results from the cast model and the plug and gate model, just to see how much the computational differences affect the data. Because this is important, because these two models are often used as references, and if they're different by more than what an IMU is to one of them, that's quite an important thing to understand. So we try to control many of the settings in these two models to try and make sure that we were using the same kinds of clinical settings as well, and so on in plug and gate, so that we had a direct comparison that was fair to the CAT model. So very briefly, the next step is to decide, after you've decided for a validation study, or you've inspected what the model calibration and computations are and how well those line up or how similar they are, it's important to choose a good movement activity for an IMU validation. And this is often overlooked because many validation studies out there simply focus on walking gait, because this is a classical traditional starting movement. But I'll illustrate to you now just the task that we chose, and then talk a little bit about the results that we found for that task, and illustrate why it was important that we chose this task. So I'm going to just jump back to the software and show you the task quickly. So here again we have the skeleton and the video, so you can have a nice view of this. We chose an ergonomics task, so we try to simulate basically a wide range of motion on all of our signals that we could, as much triplanar motion as possible. So we tried to have instead of just having sagittal plane motion, we tried to really stimulate motion in the transverse plane and the frontal plane as well. And so so this is an important thing that I will highlight later in the talk as to why this was important. But I think this was really an important step for us. So how did we analyze the data from these two systems? So basically, an important thing to start off with, I think, is just to look at signal and error curves for individual trials, because this really highlights differences. So here, for example, you see our CAST reference system with our optical data for the hip flexion for this ergonomics task, and we just looked at the first 10 seconds. So we've zoomed in a bit. What you can see there is that we can calculate our direct error curve over those 10 seconds by just subtracting the one signal from the other. Now, this is where it comes into play that you must really check things like signal polarity. Sometimes models have positive for flexion and negative for extension and vice versa. And it's important just to check all your signals to make sure that the polarities are correct. Otherwise, your error signals obviously are not correct. But another hidden issue here is time synchronization. So clearly you have to measure with the two different systems and then line up your data in time. If you didn't do that correctly, for example, this shows now how the error would increase artificially if you had a 200 millisecond difference in timing or error in synchronization of your two data streams. Now that's the sort of size delay you would get from just a USB delay if you clicked record at exactly the same time on both systems. Somehow miraculously, you'd still probably see a variable delay of a couple of 100 milliseconds. And that obviously leads to quite significant error, up to 20 degrees in this case. But if you're also lining up your data in a software, using a software approach, it's important because you could, even if you make small errors in sync, maybe like in this case, you can see a 25 millisecond difference. It is not very visible here at the top, but it's already increasing the errors by 1, 2, 3 degrees, which is quite important in a validation study. So I would really recommend that you do a hardwire sync between the two systems, because this really allows you to get a perfect synchronization of your data. Now, this is where it gets quite interesting when we talked about computation of models. So if we overlay the optical system with the plug-in gate results, we see something very interesting. Something quite shocking, actually, for me. I found this really shocking. So what you see is that the optical system with the plug-in gate is very similar to cast when the hip is not flexed. The results look really good, as you can see here. But as soon as the hip is flexed, the red line simply just starts to deviate from the reference. In other words, with exactly the same landmark calibration from your cameras and exactly the same input data from your markers, we're seeing a big deviation just from the difference in model computations for cast and for plug-in gate. But we're only seeing that at extreme ranges of motion and in a triplanar motion. This is really why we chose a complex high range of motion task, to try and really see what happens at the extremes of motion and not only in very similar postures to walking. So for example, if you just look at the range up to about 50 degrees of hip flexion, if you just stayed within that range, the optical system for plug-in gate and for cast would be very similar, and they'd be. But if you were comparing your IMU system in a validation study to plug-in gate, it would look very good for walking. But if you had a squat or something with a lot of bending, suddenly the results look bad. And yet when you check against cast, it doesn't change. The error stays very stable. And I believe that that's because the direct kinematics that's being done by cast is much more compatible or comparable to what an IMU system does. In other words, that whole effect of passing the hip center down to the knee center, to the ankle center, this is the kind of thing where if there's a lot of soft tissue artifacts, in other words, that this posture is very different to the posture that was used in the landmark calibration. And that may explain some of why we see a variable error. So there's hidden modeling effects that we need to be sensitive to, and to understand how our models relate or how they interact with the protocol that we've chosen. This is a good example of that. And there's also hidden statistical effects, for example, sensitivity to time. I mean, if you looked at the error for the optical plug-in gate system in this time box, it would be something like 5 degrees, perhaps on average. If you chose to move it on a little bit and include more of the neutral posture for the hip, you'd get a less big error. And if you chose a position of or if you chose mainly data that's in the neutral posture, your error would drop significantly. So it's really important to understand the distribution of movement and different postures within your trial. Because if you had, for example, an extra minute of standing at the end of your trial here, you'd actually just reduce your error artificially. So these are just interesting things to do with individual trial differences. Now, common validation outcomes that we can do with these outcomes, with these error signals, I want to walk through these, but I just want to first explain that we've added an extra graph here. This would be the IMU system calibrated with the static pose calibration. And so we see an offset in the blue line compared to the green and the black line, which is our CAT and our cast. And it's really interesting because it has an error which is more of a constant offset error than a variable error like plug-in gate. And so my point I want to make here is that we really need to be careful that we capture the performance of the IMU system, for example, with the static pose correctly, because it's actually tracking the motion really well. It's got the same pattern throughout. It's just got an offset error. And so when we choose metrics for our validation study, or when we're reading validation outcomes, important that we look for these different aspects. So for example, we do want to know absolute error. How different on average is the signal from the reference? And we'd use something like RMSD or mean absolute error here. But it's also important to be fair to an IMU system that perhaps is tracking motion patterns very well, but is just using an inferior or different calibration procedure, which is still reliable and useful. It's just not very well comparable to the other type of calibration. So you need metrics that look at shape and whether the shape of the error signal changes over time, because if there's just a constant offset, perhaps it's not so bad in practice. So there are different things you can do there, standard deviations of the error, correlation analysis, and so on. And there are other more standardized methods for doing offset analysis in these kind of validations, Bland-Altman, limits of agreement, and so on. Or you can just take the mean of the errors. Sometimes that's also important to see if your system is always lower or always higher than the reference. So trends or offsets, the direction of the offsets is also important to consider. And then you might want to know, well, how bad can it get in general? So if your plug-in gate looks quite bad, but it actually is on average perhaps half as bad as it can get. So if it's up to 10 degrees wrong, you might want to know that. So I think it's important to also look at maximum errors in these validation studies. And perhaps more modern approaches such as SPM, statistical parametric mapping, can help us find out where are those differences happening in the movement. So I just want to spend the last 2 or 3 minutes looking at the results from our validation study, because now this is the group analysis for 10 people that we analyzed. And we're looking at the root mean square difference between, at first, just the IMU with a static pose and how it differed to cast. And what we see here is actually quite an interesting picture. Some of these angles we're just looking at the hip, knee, and ankle in this case, and for our 3 different planes of motion. And what you can see is that some of the signals are actually still, even with the static pose calibration, below the minimal clinically significant difference. We see obviously hip flexion is a bit high, and we see transverse plane is quite a bit above 5. But in general, some of these angles still compare quite well in some cases to the cast model. And if we do the CAT calibration, I thought this was a really good result. What we found here is that basically when you apply the CAT calibration, you get below minimally significant clinical difference for all our angles. And so the calibration really has made the biggest difference here, or has made a big difference here, because it's made the data comparable to a gold standard motion capture system. Even though we're measuring the landmarks using a different system, the CAT system instead of the cameras, and we're measuring different technical frames with a different technology, we're still getting errors, RMSD, within 2, 3, 4 degrees error. And I think that's quite promising. We were quite happy with these results, and it was really eye-opening to see that if you add the Vicon data in here and you look at how different the plug-in gate model is, in some cases it was even more different than the static pose IMU data. Although these are angles that we know that plug-in gate traditionally doesn't measure that well. But in some cases, there were still differences between the optical data of the same sort of range of error, 2, 3 degrees. And this just shows that when you're comparing IMUs to camera systems, if you're getting in this range of error under 5, you're literally in the same range as you have difference between models for using the same camera data. And so I think that's a very interesting topic of discussion to bring up in when you consider these validations, is what is valid. And the last point I just want to make to show a last bit of data, this is random errors relative to reference. So we saw that the blue line had this offset in the hip flexion, and you see that reflected in the RMSDs. But if you look at the hip flexion data in terms of its shape, then it shows that the IMU with the static pose is actually really good in terms of tracking motion patterns. And I think this is important also when we talk about validating IMU systems, is that we don't need to have a landmark calibration to be able to use an IMU system. It's obviously much more desirable to have it if we can, because it gives us ISB recommended data, ISB compliant modeling data. But the IMU system performed really well, given that it had a different calibration, the static pose. And you see this in this data, that there's very little random error in the signals, because the IMU system is tracking the range of motion, and the only difference is really the offset error. Well, that's the major difference that you see in the RMSD data. This just illustrates that it's very that the IMU hardware is working well. So that's it. That's the summary of the talk, really, is we've looked at all these different factors, and I'd leave these questions on the right-hand side of each factor, just something that you can think about to help you consider the different factors that have affected the data, just so that we can have a fair comparison between IMU technology and optical systems. And I think generally, in summary, if they both measure the same thing, that's really good for both technologies. It gives us confidence that we're measuring something reliable. If we get the same result with two different systems. So that's it. I'd be happy to take some questions if there are any.
Great, John. Thank you so much for presenting this information. We do have a couple questions to get started. First, is the MCID value applicable in all planes of kinematics? Do you have any information on that?
Zach, just to say, your sound's coming through a bit unclear to me. I did hear the question, but it sounds like there's some sort of fan or interference. I'll go ahead and answer the question, though. I think that's a very good question. It's not something I've considered very deeply, but if I just think about it, I think it should be considered that some joints obviously have a much lower physiologically plausible range of motion. I mean, if you're talking about knee rotation, for example, or knee varus valgus motion, 5 degrees is already quite a big chunk of the actual signal that you'd be trying to detect in a healthy knee. And I suppose then that 5 degrees sounds a bit high for that kind of scenario, but at the same time, I think we're dealing with the noise and uncertainty that comes from so many different factors, the calibrations, the measurement accuracy, the computations, that I don't think we can lower that value for certain joints. I think if we think clinically, I would imagine that this is starting to get to the range of motion that you can detect with your eye, 5 degrees. So I think if we had to lift it, it also probably doesn't make sense in terms of allowing more uncertainty than what the eye can do in a visual observation. So I don't have a confident answer for you, Zach, but I do think that we can't lower it very confidently to something like 1 or 2 degrees. I don't think that that's very feasible in a clinical setting to get that kind of confidence in your data. But I don't think that making it higher helps either. So I think 5 degrees isn't necessarily the right answer for everything. I just don't know what the right answer is.
Is my audio better?
Now it is, yes. Did you hear my answer?
Yes, I did. That was perfect.
Okay.
Next question. How long was it taking you to set up the sensors and to perform a calibration, including the digitization of all of the landmarks?
That's a very good and perceptive question. It took very long the first time, Zach, because I think these things are quite tricky, and you'll see with your validation studies that you've really got to plan a couple of pilots and get it zoned in, because I think the first time we did it, we were really ambitious and we tried to do it. I think it was, I'm thinking now of the setup time and not the capture time, because we had a bunch of different tests actually that we did in the activities. But if I just look at setup time, I would think, you'll notice from the photos, we also did a full body. So we were putting markers on. I think it was something ridiculous, like 100 markers, or in that region. It was so many markers because we had to put on the arms and on the sensors and the clusters and so on. So it took a really long time. I would think at least an hour for putting just the markers on for that whole marker set, because we had to strap the sensors on and so on. And then I would say the digitization is actually quite quick once you've got it sort of working well, streamlined. You know, it's much quicker than putting the markers on, because we mark the points. So palpation time takes long if you're doing the full body, but when you're just doing the CAT system, it's actually quite quick. So you know, the validations are really nitpicky scenarios. I would say you could do a lower body digitization, strap the sensors on and be ready to go in like 15 minutes if you were just using the IMU system and the CAT system. But because of this whole kind of detail around putting the Vicon markers on and everything, I would say that took at least an hour and a half to be ready to start testing. So it was, I might be underestimating that. It would vary, it got better with time. But we were looking at like 2 hours plus for a test, including capturing the data and breaking down again afterwards, closer to 3 hours in the beginning.
Wow. Okay. So definitely
That was a large investment of time for the validation.
Right. Right. So
But
the combination of the system, the combination of the systems certainly adds to it. And obviously after developing proficiency in either of them, that's going to speed things up. But you said that just using the CAT system with the motion, you're able to get things, a full body set up in under 15 minutes.
I would say maybe a little bit longer, 20 minutes
okay.
for a full body, and a half body, probably 10 to 15 minutes. If you strap the sensors on and you go, something like that.
Great. Okay, moving on. So we have one that says, since there are multiple calibrations when using IMUs to minimize drift errors, does the calibration adjustment tool need to be used each time? And if not, then why?
Okay, so I just want to clarify the difference there between calibrating an IMU and calibrating a kinematic model. I think that's important for people to understand, because you have a bunch of different calibrations for IMUs. Some are done in the factory just to get everything sort of ready for initial use. And then you can run certain procedures to recalibrate IMUs for doing sensor fusion as well as possible. But the question about CAT and calibrating the model, basically what the anatomical calibration is doing is it's trying to find where the landmarks are, or the body is, relative to the technical frames. And so you've stuck a sensor onto the skin, and now you want to know, how do I get to the bone from the sensor? So you need to, so calibration is only valid while the technical frames are still stuck on the body in the same way that they were when the calibration was done. So if you calibrate at the beginning of a test session, and then you'd only need to do that calibration once. But if you took the sensors off and put them back on again, you'd have to redo a calibration for that same person, because the positioning of the technical frames on the body has changed. So you don't need to do it every time you record one activity, but you do need to do it every time you strap the system onto someone, because of the different position of the sensors on the body, the potential difference.
Okay. Quick question from the chat. Somebody is asking, so in the Neuraxon manual, we recommend sensor placement on the frontal side of the segments for the thigh and the shank. Are you aware of differences in placement? So if we were to perhaps place the thigh sensor on the side of the thigh, and are you aware of any studies that maybe compare the effect of the different placement of IMUs with regards to the kinematic variables that might be calculated?
I'm aware of some data that has been collected by some colleagues. I'm not aware of, to be honest, no, I'm not aware of a published peer-reviewed article on this question, which I think there might be one. I just haven't seen it. But if there isn't one, I think it's a really important question. Soft tissue artifact is by and far the most important factor affecting the validity of most motion capture systems. And I mean, many studies have been done on the optical technologies around how certain markers move on certain points of the body. The problem with that is that it actually varies significantly between people. So there's no sort of best, there are recommended positions for certain placements of markers that are just generally more or less reliable, but it actually varies on the build of the person and especially the distribution of soft tissue on the bone. Some bones are worse than others, so the thigh is traditionally a very difficult one to track well, but the shin is usually, you get much better tracking between the technical frame and the shin bone, or the shank or the tibia than you'd get for the femur because of the thigh muscles. But for IMUs, I think generally speaking, IMU technology is just not as well covered by these validation questions. It's not really as well researched, and I really recommend and encourage people to do these studies if they haven't been published, because I do think there's a big difference between, and it might be that certain placements are more recommended for certain movements. So if you do a squat, it might be better to put it in the side, say, and then for running, it might be better on the front because the muscle contractions are different and so on. But there's no hard and fast answer for these things, unfortunately.
Yep. Great. And let's see here, moving along. We've got quite a few questions that we're working through. So thank you everybody for submitting them. We will, just to reiterate, we will be sending out the recording of today's webinar to everybody that's registered, including the question and answer portion. So if you do need to jump off, please feel free. I know we are nearing our end of our time point for our hour, but we will get through the rest of the questions and address them live for those of you that are able to stay on. So the next question is based on the validation work that you've done with landmark calibration using IMUs. Would you be confident in using IMU-based motion tracking for clinical analysis of a pathological populations? So folks with cerebral palsy, maybe prosthetic patients, even those who may be diabetic or obese patients.
Yes. Okay, so there's two answers to that question that come to mind. The first one is, depending on what you're interested in measuring, I will say this, I'm quite confident that if you can get the kinds of results that we got for the postural information, in other words, if you're interested in kinematics of joints and so on the level of joint angles, I believe that the main Achilles heel of IMUs has always been that we just cannot get the right landmark calibration using that technology. And with the CAT system, it really feels to me like a massive breakthrough for IMUs, because to be able to get that calibration means you can get very close to what you'd get with an optical system, which is what people are using for these services, these clinical services. But I must also just add, for those that are not so familiar with IMUs, that we know that IMU technology is still developing, and one of the construction areas where we're still trying to get very close to the camera systems is the translation information, number one. So if you're interested in step lengths and gait speed measurements and things like that go with this. So the temporospatial output from IMUs is still not as accurate as camera systems, and the jury is still out whether you can use it for full-on gait analysis like that. So joint angles, fine. Translation is still, it's okay, but not great yet with the IMU systems, and companies are working on these solutions as well. So I see a future where we'd be able to do it. I just want to also comment on researchers or people who are trying to do anything to do with kinetics as well. So if they're trying to do modeling of more than kinematics, trying to get joint forces, joint moments, any kind of modeling that looks at anything other than the postural information. Obviously, IMUs are still also not able to provide that kind of information in the same way as a camera system. So in short, it really depends what you're trying to do, but I am very confident in the kinematic outputs using a landmark calibration, because the IMUs track the technical frame very well.
Great.
Maybe Zach, just a last comment on that. It's also important to understand the limitations of IMUs. Some systems really don't measure well in a magnetically disturbed environment. So it really also depends where you want to do these measurements with IMUs. The technical frame tracking, as we saw in that one picture I showed, really depends, the accuracy depends on best practices. So I would also just add that caveat as well.
Yeah, certainly a great point to make. With kind of playing off of that question with regards to landmark calibrations, what would be some adaptations, or have you made any adaptations in previous work with these clinical populations? You know, sometimes the access to these landmarks may be challenging or not possible. What would your recommendation be in that case, if you have one?
So we've had these problems. This is a classic problem, you know, things like central obesity and so on, where you can't get access to certain pelvic markers and so on. These are the classical ones. This is the same problem we have with optical systems, and I would say the same sorts of solutions would would be useful. I mean, if you're able to somehow just get, using the pen, access to that landmark just for that moment that you're doing the calibration, you don't necessarily obviously need the person to make that landmark available in a compromising way throughout the testing. So I would say, if you can't get the landmark, it's the same problem for both technologies. You know, you just I don't know, we've had some crazy things happen in our lab, just funny situations where we try to move people's soft tissue around, and it's a delicate scenario to deal with. But no, I don't know of any specific solutions that are specific to the CAT system. The CAT system just operates in the same way as a camera system. It tries to locate a point, and if you can get that point just for one moment, that's enough often. So you have to be creative and sensitive as well.
Certainly. Moving to more modeling side of things, would you expect that the CAST model could potentially also benefit from something like the calibration adjustment tool? Do you think that it would even improve the gold standard performance of this model? Since the way that the CAST model sets up the segmentation?
No, so I wouldn't put it like that. I would rather say that basically the modeling that's done by IMU systems is in fact quite similar to CAST. And what you're basically doing is giving CAST information from a camera system or from the CAT system that it can use to estimate where the anatomical frames are. And so it's not really, I wouldn't say the CAT data is in any way superior to optical systems. I think we know that the landmark uncertainty on the CAT system, which is actually an important factor to consider, is around 3 to 4 millimeters, which is quite a bit higher than optical systems. They're sub-millimeter accurate. So the accuracy of the data coming from the CAT system is not superior to what CAST is used to getting from a camera system, and it's not necessarily different. So I would just say that it's important that IMU systems that use landmarks are perhaps, that they could perhaps use then the CAST type of modeling approach, rather than saying that the CAST model can be improved. I would say IMU systems can be improved by the type of modeling that CAST does.
Great, thanks. With regards to using the calibration adjustment tool, is it necessary for the patient to stand still? And how do you make sure that there's no movement while doing so?
Yeah, that's a very good question and a very relevant concern. So because, and can get quite technical, I'll avoid the technicalities just to say that basically, whereas a Vicon system measures all the points, or a Qualisys system, some other camera system would measure all the landmarks during a standing posture at exactly the same time, the person is rightly perceiving that the CAT system is measuring them one at a time. And so there is the risk of that. And basically, right now, as I understand it, one of the construction areas around the CAT for any upgrades would be to try and make it not necessary to stand still for the entire digitization, but perhaps to stand still for certain segments at a time, which would make it that would be another breakthrough for the CAT. Unfortunately, right now, our patients or subjects did have to stand still, and it's a couple of minutes, 1, 2, 3, 4 minutes that they have to stand still. So if you're doing a lower body, perhaps it's not such a big deal for healthy people. For patients, I can foresee that it might be challenging. And the one thing I can say is that perhaps is that they don't have to stand unaided. So I think one of the things we try to do was have something that the person held onto. But this is definitely a limitation of the CAT system, is that it measures one point at a time. We didn't have huge problems, as you can see from our results, but in clinical practice, this is something you'd have to practice and get good at, so that you can get through the points quickly and help the person by maybe stabilizing them, having them hold on to something while it's being done.
Got it. Yeah. So just positioning the subject into somewhere that they're comfortable, but also allows you to access the different landmarks would be the recommended setup situation.
Yes, as I mentioned, you don't want to calibrate in a very, very strange posture that you're never
Right.
going to test in. But because of the soft tissue differences between those two postures, you might have some problems. But generally, you can have a person sit down or do something other than stand. But if they're standing upright, they could hold on to a guide rail or some other.
Sure.
We used a chair, and this helps quite a lot if they can just hold on to something.
Great. And then we have a question with regards to looking at precision measurements. In your opinion, which system would be better for looking at the precision of small movements versus large movements together, like, I don't know, the wrist versus the shoulder?
Which system, as in like the IMU system or the camera system?
Yeah, I suppose between those two.
That's a good one. I mean, IMUs are very sensitive to small motion, small movements in terms of, the sensitivity of IMUs is, I would say, just as good as the camera system. If you're talking about if the technical frame moves just a little bit, I think both systems are really sensitive, but the camera system is obviously more accurate within it. So, the precision, I would say, still belongs to the camera system, definitely, because you're getting sub-millimeter accuracy. I would just say, though, an important thing I didn't emphasize a lot is that if you have small parts of the body where you have lots of little markers close together, there's sort of geometric properties of these technical frames that when you construct those technical frames with markers, if they're very close together, the markers, then the accuracy starts to drop a little bit because the lever arms of these vectors that you're using to create that coordinate system are very sensitive to small marker deviations. But if you have a sort of a large cluster, then I would still say camera systems are quite a lot more superior for picking up, not for picking up small motions, but for picking them up accurately. And that's the difference. I think the IMU would pick up the motion as well, but there's just not as much precision. I mean, it's still quite good, 1 degree per axis, or maybe even slightly better in some cases. But the camera system is just, it's the gold standard.
Right. Well, and then as discussed, I think it also depends on what you want to measure in terms of these movements. Is it the ranges of motion, or is it the translational elements? And so you have to take that into consideration as well.
Yeah, true.
One more question, and this is with regards to using the calibration adjustment tool. Does the CAT system need to be near the participant for each activity? If, for instance, if you want to collect data at multiple locations, would that be a problem? I've got a general response for this, but I'll let you discuss it first.
So basically, just always remember that the calibration is only needed to get the configuration or how the sensors are placed on the body. And once you have that information from the calibration, and the person can go anywhere, they can do any kind of test. They can move away from the CAT completely. In other words, the CAT doesn't track you when you're moving. It just gets that snapshot at a point in time. And as long as the sensors stay stuck to you in that same configuration, you can now use the system as you would have before. You just have a better calibration in terms of using landmarks than you did not. So the range is important when you're doing the calibration. You need to stand near to the CAT system within a 1.5 to about 1.5 meter radius from that system. So you have to stand next to it because it's a magnetic tracking system. So the accuracy is better the closer you are. But once you finish the calibration, there's no need to, you can pack the system away if you want, the CAT system. It's not needed anymore.
Perfect. That was exactly what I was going to discuss as well. We had one more come in. Are there any benefits to using both inertial and optical tracking systems together?
I think so. I think this is kind of the future. Hybrid motion capture systems are, because these systems actually have different strengths. In fact, one of the things that many people don't think of is that IMUs actually measure things like acceleration more accurately than a camera system because they measure it directly. And so we know that the camera system is superior in terms of positional tracking. The IMU system measures the derivatives of those positions more accurately. So I think companies definitely are looking in the future to try and combine them. I mean, camera systems need line of sight to the camera, but an IMU can be put under a jacket or can be obstructed from, it doesn't need any kind of field of view. So you can, in a cluttered environment, I think it's much the same as how GPS systems use IMU systems to fill gaps in data and so on. When you go in a tunnel and the GPS is no longer available, the IMU system fills in. So I think these kind of hybrids are the future because these technologies have their own advantages, and if you put them together, I think you can only get better.
Very well said. Very well said. Well, that's it for our questions. Again, I want to thank everybody for attending today. Really appreciate it and hope that this was an informative and useful discussion of IMU technology and its comparison to optical motion tracking. John, thank you so much for putting this together for everybody. As I mentioned, we will have the link to the recording sent out, and it should also be available on the Neuraxon website. If there's any further questions after digesting some of the information from today, please feel free to contact us at info@neuraxon.com, and we will be happy to address any further questions. We'll go ahead and end it, and I appreciate everybody's time and hope you all have a wonderful rest of the week. Thank you.